Assalamu alaikum. I am Omar Beg. Today we are discussing about the third part of mass spectrometry, gas phase ionization. These methods rely upon ionizing gas phase samples. The samples are usually introduced through a heated batch in an inlet, heated direct insertion probe, or a gas chromatograph. Some general remark on ionization when an electron with an kinetic energy EKIN of about 50 eV passes through a low pressure gas mixture as in the ion source, an actual collision with a neutral molecule is not likely. The repelling force of the valence electron can be overcome when the kinetic energy is in the order of magnitude 10 6 volts. Therefore, an electron will pass in short distance of a molecule. A 50 eV electron travels with a speed of 4.2 10 powers 8 centimeters per second and passes a molecule a few nanometers wide in about 10 minus 6 seconds. Due to passing electric field, the orbit of the valence electron gets disturbed to such an extent that it may lose one valence electron and ionization occurs to give the radical cation of the molecule with molecular weight m. If the weight of the electron is too much high, it will on the upper side. If the it will upper side, and if the weight of an electron is too much low, it will on the lower side. The capture of an electron by a neutral molecule is unlikely to happen. In practice, it appears that in about 10 to power 3 to 10 to power 4 of the formed positive ion, only one negative ion is formed. The ionization time is of 10 minus 16 seconds are the fastest vibration in organic molecules. Such tests indicate that the position of the nuclei may be considered unchanged during the process of ionization. The ionized level is recharged through a so-called Frank-Kendall transition. The head area arrow A in figure. As a result, a molecular ion is formed with several possible vibration states. Some of them are at a high energy than the dissociation arrow C, so that fragmentation occur. A Condon transition can also allow molecular ion in a higher electronic state to be formed. These will dissociate even easier because of a decrease of depth in potential energy curve, and because the minima tend to drift to higher into nuclear distance. If we have to change the radius of the if we have to change the radius of the electron, we have to change the field of the magnet and magnets. In polyatomic molecule, the change of potential energy curves with changing into nuclear distance is such more complicated. More oscillators are present, and the curve will intersect at several points. If we take acetone as an example, as focus on the carbonyl, we can distinguish three types of electron, namely n non-bonding and electrons. Their respective energy level are depicted in figure 1.6. This reveals that the probability of electron release during ionization decrease in the order n greater than pi greater than theta. The ground state of the molecular ion of the acetone will be the one where an electron is eliminated. The first and second excited level correspond to a missing theta or a electron. If we have hydrogen atom, so there are three types: protium, deuterium, and tritium. The majority of the molecular ion of acetone will lack a single electron, and subsequent formation of fragmentation ion has to be explained from there. There is a valid even if the primary ionization was due to removal of a pi or electron. These ions cannot eliminate an excess of internal energy E. through collision with the other molecule because of their formation in high vacuum. In the case of acetone and especially in larger molecules, it is very probable that the energy curves of the first and the second excited state of the molecular ion intersect. At the intersection, the molecular ion can change in excited state without energy loss. This radiation-free transfer produces a highly excitable molecule ion in the ground state, which makes it even more prone to dissociation.